Hello everyone, today we are going to develop a simulation of a centrifugal pump, both impeller and volute, as shown on the screen. In this case we are going to use Ansys CFX. To develop this simulation we need some files, which are going to be in this compressed file, which you can download from the description of this video. The files contained in this compressed file are centrifugal pump in IJA's format and step format. They are the most common formats used right now in any CAD software, which you can also modify. In addition to these geometry files, I am also sharing with you a mesh in CGNS format and MSH format. For this simulation, we are going to use the mesh formats directly. However, if you want to make any scale modifications or you are proficient in any CAD software, you can use the IGES and step files to make the relevant modifications. In this case, the mesh I am using contains more than 1 million elements, which means that it is necessary to have a research license or a commercial license. Although some of you have also obtained valid licenses on the internet. I am telling you this so that you take it into account when starting the simulation. But it cannot be a problem either, since with the geometry you can adjust the mesh elements for your simulation without exceeding the configuration that comes with it by default in Ansys Academic, which is the free version. That said, we are going to start with the simulation. After downloading the file, you unzip it, open it, and you will have access to these 4 mesh geometry files. In this case we are going to work with centrifugal mesh.msh for the simulation in Ansys. However, you have here another mesh file as well as I mentioned before, the geometry files for modification if you think it is convenient. After that we go to Workbench. Here in Workbench we are going to work in Ansys CFX. We go to CFX, we drag, we drop on the canvas. Here we go to Setup. We right click and we are going to select Edit. For this case we are going to work directly with Mesh since it is built and includes the boundary conditions. Remember that if you want to do the simulation from the beginning, you have the geometry file with which you are going to place the boundary conditions according to your needs. We go here to File. In this case import mesh, and I go in this case to the desktop where the centrifugal file is mesh.msh. I select it, I click on Open. I wait a few seconds for the file to load and I already have the mesh file ready. In this case I go here, right click on Mesh Statistics. And in this case the number of elements is approximately 2.5 million. Remember that with the geometry you will be able to adjust these parameters to have 1 million elements or less as required in your simulation. I will click here on OK and we are ready to start the simulation. This file is made up of 2 geometries. One is the impeller and the other is the volute. What I am going to do is divide these geometries into 2 parts, and I am going to do it here from Flow Analysis 1. By default it is default domain. We are going to right click here. Insert. I am going to click here on domain. Here I am going to click impeller. I click on OK. Here I am going to select the impeller, and in material by default it is air. This is a pump that is going to work with water. I am going to select this material, and also this impeller is rotating, with which the movement of the domain is not, it will be stationary, otherwise it will be rotary. We will give it an angular velocity of 1600 revolutions per minute. You can use the units that you think are convenient, also the angular velocity that you think is convenient prior to calculating your design. Here the rotation axis is on the z-axis. It is important to look at the direction to avoid any error, especially with the positive-negative sign of the angular velocity. Observe where the z-axis is, in this case by the right-hand rule the direction is correct, so it would be positive. I go to the next tab of the fluid model. There will not be heat transfer, I put none. I will leave it in this turbulence model, share stress transport SST. You can modify it, although I suggest you leave it there. An additional mesh refinement would have to be done. if we work with this turbulence model. But for practical purposes of understanding how the simulation works, it is more than enough. There is no combustion, there is no radiation issue, we apply it. Finally, okay, ready. Now we have our two domains. Here we have the impeller that says default domain that was by default. We are going to change its name. I am going to put volute. Ready. The volute is easier to configure. Then select volute, and this area will be the exit area. I right-click. Insert, and in this case the boundary condition is going to be exit, outlet. Here some names are already configured. For example, here is already outlet because the mesh was already created like that, which makes it easier for you to develop this simulation. We go to the next tab of boundary details. Here by default is the static pressure. What I am going to do in this simulation is to place a pressure condition at the beginning and a mass flow condition at the exit. For that reason here the exit I am going to place mass flow, and in this case I am going to consider 77 kilograms per second. Why do I put this value? It had previously been designed for this mass flow condition. Remember, for scale issues, for geometry issues, for calculation issues, you can work with the pump that you have designed by modifying the values of both pressure and flow, or guide yourself also from some characteristic curve as you see fit. I'm going to apply it and then OK, perfect. Then what else do we have here? In the volute we have the wall condition. Also, as they are two volumes, we have areas that are going to be in contact. The stationary part that comes to be the volute. I'm going to enter volute again here so that you realize that domain motion. Domain motion is stationary since the volute does not move. While in impeller here we do have a rotation of 1600 revolutions per minute. Then we leave here the volute, which is stationary. And the area that is in contact with the impeller, we have it to configure in the interface that is here at the bottom. You select interface, right-click, insert. Domain interface, we'll leave it with that name. I'll click OK. Here it says the type of interface. In this case the volute and the impeller that we are visualizing here are negative. They are water flows, they are not solids, therefore the interface will be fluid. We are going to select our first computational domain, that is the impeller. It is selected here, and in this case the impeller has different names that have been previously configured. We are going to select this last one, pass contact region target. Target region, that is the green color that is on the side. Here the theme of the blades is selected, but here the important thing is that only this list appears. We go to the next condition, that is the impeller that loaded by default. We are going to change this. For volute here we are also going to choose another region, that is the pass 1 contact region source. One is source, the other is target. Very well. Then if we select both, we realize that what is going to be selected? The interface of both volumes or both geometries, which remember are fluids, impeller and volute. Now in this case, in the lower part where it says interface model, the connection is general. In this case we are going to leave it so because we don't have a periodicity condition, and what follows is the frame change or mixing model. Here we are going to choose frozen rotor. Why do we choose frozen rotor? Frozen rotor is chosen when you are going to simulate a turbomachinery in a stationary condition. The rotor is going to be frozen rotor. But we are going to make a small configuration so that the software understands that there is movement in this area. Finally, in this pitch change condition, we are going to change the value here, which is the area in contact. Since I have two areas that are in contact, 100% of their faces, and that is why here I am going to put the value of 1. I hit apply and then OK. Ready. With that I already have the configuration of the interface. Then the volute. What else do we have? We already configured the outlet. We have the wall of the volute here, and we have the interface. If you want you can change the name here. I am going to call it wall here so as not to get confused and know what the wall is. The volute and the configuration of the volute is now ready. Now we are going to focus on the impeller. In the impeller it will have an inlet area, that is the area here. This upper area, you right-click on the impeller. Insert boundary here, we are going to choose inlet. Inlet is already loaded by default. It is a stationary condition. We go to the next tab. Here I am going to place the pressure condition. What pressure? I am not going to place static pressure but total pressure. This total pressure, you know that it is the sum of the gauge pressure plus the atmospheric pressure. I am going to consider for this simulation, for this case, the condition of 1 atmosphere. This value is also going to be changing, and it will depend on whether the water reservoir is up below the pump axis. No, you know that it can be a negative or positive pressure depending on the position of the pump. You can also calculate the NSPH if what you want is convenient. For practical purposes, we are only going to consider 1 atmosphere and remember to place here in total pressure. We do not make any more changes here. I am going to hit OK and that's it. We already have our input condition. What else do we have here? We will be able to divide it to better visualize it in the CFD post, and we will now select the blades. Right-click on the impeller. Insert boundary. Here I will place blades or blades. The blades are wall conditions. I will place walls, and here I already have the blades defined, which are like this. In this case we have 6 blades defined. Here you can see that since the condition or volume has been a rotation of 1,600 revolutions per minute for the impeller, here by default it appears rotate. We will leave that like that. We go to the next condition, and in this case it is a non-slip condition. Everything is fine. We apply it and then click OK. Perfect. We already have the blades here. What else is going to rotate in the impeller? In the impeller, the shaft is also going to rotate. So we select the impeller here, insert. We will place axis here, which is the shaft. It is also a boundary condition, a wall condition, and in this case it is the fixed condition. 2. That is the axis. That axis is also going to be in motion, or at least we are going to consider it that way. That is why the rotating condition also appears here. In the next tab, we are not going to make any more changes. Apply and OK. Ready. Now the drivers for visualization effects are also configured as a lower zone and a zone. Upper, the lower area is called H. The upper area shoot, and if you want you can place it, if you want you can leave it like that. In this case, for visualization purposes, I am going to make the corresponding configuration. I am going to call it hub here. It is also a wall condition. Practically everything is wall here, and I select here, I already had it configured as hub, which is the lower area, which is better appreciated here, that area that will be in contact later with the axis. I am going to call it H. It is also rotating together with the entire impeller. I hit apply and OK, and then I continue with the configuration. We are going to hit shoot here. It is also a wall condition. I select that option, which is the upper area. It will also be rotating. I hit apply and then OK. Now what we have left is the following. I am going to select impeller default here, which is what I have not yet selected and which is painted in green. This area that is shaded in green is the area that will not rotate at the angular speed that the impeller has. For what reason? Because that it is the fixed connection. Right, and this small space here is called tip, which is the space between the impeller and, let's say, the connection it would have with the volute. That is not going to move either, they are fixed zones. But within it the flow will be moving at the corresponding speed. So since that zone is fixed but belongs to the impeller, we must make a configuration to counteract the angular speed of the impeller. How do we do that? We are going to divide that as well, and we are going to call the first part the fixed zone. Here I am going to call this fixed. It is also a wall condition, that is this zone here, right? And this zone here, as it belongs to the impeller, it says rotating. We go to the next tab, and in the next tab it goes to activate this option that says wall velocity. When you activate wall velocity, it says counter rotating wall. That is to say that while this rotating here makes the impeller or this area rotate at 1,600 revolutions per minute, what this option will do is counteract that speed so that they cancel each other out. Therefore, this area that is shaded in green will not rotate. It is automatically cancelled out. We apply it and then OK. The same is done with this tip area that is both in the upper area and in the lower area. That part does not properly belong to the impeller or the turning area. So I am only going to change the name. Here I put rename, I am going to put tip. Here it is, enter. Here it says rotating. I go to this option here. Wall velocity and I put control rotating wall. I apply it and OK. Ready. Now I have the pump ready to simulate. I do not need any other configuration. In this case the simulation is stationary. We can also do a simulation in state. Transient for this to turn, but that will be later. Now let's focus on this. By the way, geometry will also be useful to you to do that type of simulations. Perfect. Once we have done that, we are ready for the simulation. We go here to solver control. We can change the numerical conditions to speed up the convergence. But we will leave it like that by default. Suddenly, if you change the conditions, it will be necessary for you to increase the iterations. Perhaps to 1 or 10,000, and it will also depend on the number of cores you have. In your computer, we will place here in 1 apply and OK. I am not going to do any more. Configuration something quite simple, quite basic. You can now go in. Even get a characteristic curve from this. We will close Ansys. CFX and now we go to solution. If you want you can save it, we will do it. For security measure I will place here Centrifugal Pump 1. I give it in save and that's it. Now we go to solution, right click, edit. Here comes the second part of the simulation. In this case I am not going to choose double precision since it is not necessary. For practical purposes, and here you are going to choose the number of cores that you are going to use. If in this case you are only using the academic license, you are going to put 4. If you have access to a research or commercial license, you can give it the cores that you think are convenient. In this case we are going to give 16 cores. And then start the run, and now we just have to wait. Well friends, after a wait of almost 20 minutes the simulation has concluded, and as we can see the convergence has been continuous. We may have modified some convergence criteria in order to speed up this process. However, the results have been as expected. We are going to give it here OK to close, and we are going to minimize this screen. Ready. Now we have to see the results. We go here to results. Right click, edit, and now we are going to view the results. First I want to see the pressures. For the pressure issue I am going to do the following. I am going to go to this upper part where it says contour. You select contour 1. I am going to give it OK here where it says locations. I am going to select the entire pump, that is, all the parts that we have used, both impeller and volute. You can drag with the left mouse button or select one by one. Once everything is selected we click OK. Here where it says default variable is pressure. I want you to observe the following. If you click here on pressure, we go here to increase the contour level. We are going to give this 60 for example. I am going to hit apply. We observe these results. However, when it is a simulation of turbomachinery, you do not have to use the pressure variable, but you have to use the following variable, which is total pressure in STN frame. STN comes from stationary, and this would be the correct pressure to visualize turbomachinery. You select it, you click OK. You leave it here in global range. If you want local, we are going to change local here. We hit apply, and now for the impeller issue. This would be the correct pressure. Why? Because the impeller in this case is going to be in a fictitious movement. Then it is necessary to use this option. Now you can corroborate the pressures of the volute. You use pressure, only total pressure, to see the difference in the results. What else can we do here? We go to calculators. We go here to the calculator function. Here in this case, we can select, for example, the mass flow, the input. The output we had that was 77 kilograms per second. Here the input. By placing inlet I have previously calculated that it comes to be 76.99. Practically 77, which indicates that the continuity is being fulfilled. The flow that enters is equal to the flow that leaves. which already gives us an idea that the simulation is correct. We would need to validate the simulation perhaps with some experiment to have the expected results. What else can we do here? Let's draw, for example, the streamlines. I go to this part where it says streamlines. I select it here. We will start from the input. I select the input zone that comes to be around here. We will increase the number of points to 120. The variable is going to be speed. I'm going to go to the next color tab. We're going to change the variable here as well for local speed, and I'm going to apply it. I'm going to hide the contours here with you can see. I have a better visualization of the streamlines. In this case, it's also important to consider the speed in steady state. You select it, we hit apply, and this would be the correct version. Because, as I explained to you a moment ago, because the impeller is spinning and it has an angular speed that we have to consider in the results. If we want to make a small animation, we go here to the top. We select streamlines. Here you can give the speed. We're going to give it a speed that is low, and we hit play, and with that you can see here the movement of the particles within the computational domain. Well friends, I hope this video has been helpful to you. You know that you can download the geometry file to make your own modifications to adapt it to your project. If you have any questions or queries regarding this, you can write to me in the comments. Greetings everyone.